So this is my intuition behind the definition of isomorphism in category theory. And first I'm gonna show the definition and then I will show with sets how it makes sense. Suppose we have object A and object B and the morphism between them. And F is going to be called an isomorphism if there exists G such that F then G equals identity morphism on A. So we do a big circle that does nothing basically, and also G then F will equal identity morphism on B, big circle that does nothing. So very simple definition, but when I tried to understand it and visualize it, I tried to use sets and I got very confused because, in sets isomorphism is a bijection, so we need to somehow have surjection plus injection. So somehow from this comes this, and it didn't make sense to me. So let me say first that isomorphism is a symmetric thing. So if F is an isomorphism, then G should be an isomorphism too. Let's go down a level of abstraction and imagine that there are two elements inside the object A or the set A. Now that's not a category theory anymore because we know what's inside the object, but again it helps to paint the picture. And of course I'm just showing a set with two elements. In an arbitrary case there could be three or any amount. So let's first start with this line right here, and after that we will come to a realization that we also need this line for surjection and injection to be implications of this isomorphism definition. So let's see now how F then G can behave and can't behave. So we have basically three situations. Arrows to A can come in this way, or in this way. So these three cases could all work, because why not? We don't know what is inside B and we don't know how G works. It could be anything because it doesn't contradict the definition. So let's go carefully through each case. And I'm not showing a case when no arrows come to A because that would already contradict the definition. F then G will just mean an empty set. So for all elements in A, we will just get nothing. That's not what happens. This case is also trivial and not possible because an identity morphism means that every object maps back to itself. That means for every object in A, it goes through F, through B, back through G, and then return. So our G of F of X should just return X for all X in A. If it wasn't coming back, then that means that this thing would just equal empty set for some X, and we again then contradict this statement. So this is already out of the way. And so already from eliminating this case, we can conclude that G must be a surjection. It should map to all the elements in A. Okay, so what about this case? Again, nothing forbids us to have this thing. Now let's go even less abstract by looking into both sets, constructing every possible scenario and seeing how it's impossible to have this case without breaking the definition. Let's suppose that B is bigger. Let's draw arrows like this. We are already in trouble because from one point there are two arrows. And that means that if this is an F, F is not a function. It is a function when from one point there is at most one arrow. And when we go back to A, and I'm drawing it on the right just for pictures not to be cluttered, we will have a problem here too. See, we have the same picture here. And then it's not possible because F is not a function and we have to have functions between sets. Maybe if we do it properly, it will work, or maybe it will show up as a third case when F is actually a function. So now let's do it properly. F goes like this. It is not surjective because there are elements that are left out in the codomain. So F is not surjective. Maybe that's fine. Let's go back to A and see we do reconstruct A perfectly. So F then G does equal identity A. It can equal to identity A. So maybe even though F is not surjective, it will be fine in the definition. But we've covered only F then G, and I remind you, isomorphism is a symmetric thing. So when we will actually look at G then F, it will not equal identity B in this case. So this is the problem, and let me show you how it will not equal to identity on B. So to go G then F, we need to start at B. Let's try to do it like that. This function now is not injective because there are two arrows that go to one point. Maybe that's fine. Let's go back, and we will encounter the same situation as before. Either F will be not a function, but we don't want that, or it will not cover the whole codomain. So that means then F is not surjective. But we discussed that we do need to cover all the points, and that's why we eliminated this case. The same logic applies to B. So what do we do then if nothing really works? This won't work. This won't work. We are only left with one thing when the cardinalities or the sizes of sets are the same. Well, unless we do something ridiculous like this, but again, then this is not surjective, and everything works perfectly here because now it's both functions are surjective and injective, and as you can see, F then G does equal identity on A, and G then F will equal identity on B. So it is really the last case, and it's only possible in this situation. That's how I like to visualize the definition of isomorphism in category theory. If you like this explanation, please consider supporting me on Ko-fi so that I can do this kind of videos full time. And for all the category theorists out there, please correct me if I'm wrong. I will re-upload the video if there are some fatal mistakes.